So you are being recorded now. So all yours.
Okay, thank you. So thank you, Professor Garg, for that very kind and generous introduction. And thank you everyone for coming here. It's really an honor for me to come again back to IIT Kanpur. The last time I was here was about 6 years ago, and actually Professor Tripathi sitting here had invited me to give a talk on aerosols. I'm not sure where I gave it, but it's somewhere on the campus. So Institute Lake, okay. And so thank you again for inviting me back to IIT, and it's a pleasure to be here. So I have to apologize to all of you who missed this festival and are coming to hear this lecture. I kind of always, when I used to listen to speakers coming in and during a social event, I'll say, why the heck couldn't you have chosen some other time to come? So apologies. I hope I make it up to you through this talk. So I'm going to talk about things happening in the climate system. I'm a modeler, mathematical modeler, so I'm looking at it from a numerical modeling point of view. But you'll see that there are a lot of things emerging from numerical models that are kind of starting to make sense about how the climate is evolving. So I'm going to just focus on that. So I want to start talking about the Earth's energy imbalance, and then the forcings on the Earth system, particularly the effect of anthropogenic human-influenced greenhouse gas emissions and aerosol emissions. And I'm going to look at it from the point of view of the energy balance at the top of the atmosphere and the surface, which has consequences for temperature and precipitation changes, and then go into future projections and predictions based upon what our understanding is of the current and of the recent past. And as I said, I'm going to use models. So these are NOAA models and also the IPCC results. Okay, so in the Earth's energy imbalance, we've had these satellites observing the radiation budget continuously for the last 20 years. And satellites give you a global picture. So you can actually try to measure what's coming into the system and what's going out of the system. So that result is you measure an imbalance or balance. So Earth should be balanced. We know that prior to the Industrial Revolution or long-term timescales, it was in balance from proxy records. We don't have satellites then. And so to begin with, this is what the satellite measures, energy in, energy out. And so it's a simple thing. You can sort of figure out and roughly, in terms of like flux units, it's 240 watts per square meter coming in, 240 watts per square meter going out, except that there is now, well, I'll come to that. And then this sort of energy flow in the system where, here it is, 340 minus 100, that's 240 watts coming in from the sun. And then about 240 to 39 is going out, and that 1 watt is represent an imbalance that's in the system. So this is how the satellite record looks like for the last 20 years. If you look at just a straight line, and what this is measuring is a trend in the Earth's energy imbalance, EEI. And so it's a delta EEI. So you're going from, the straight line is giving you about a watt per square meter of increase in energy into the system over the last 20 years. We haven't had, unfortunately, a satellite record which goes back prior to about 2000. So we only have measurements from about actually 2001 onwards continuously. And so this is a clear indication, and this is a very robust thing. It's sort of observations, and it's been verified from a number of sources. And so it is something which is pretty serious. I mean, there is an imbalance growing in the system. And so why is it increasing is the question. And sort of to make a long story short, I'm going to sort of show later on, this is due to anthropogenic influences over the last 20 years. And the net result of the imbalance is, if you look at the right side of the diagram, 91% of that energy is going into the oceans. So the oceans, because the water, can absorb heat and retain it. So 90% of that heat is going into the oceans, and there's some other going to land and ice. But that ocean warming is now a big catalyst in terms of climate change. So going into some of the observed changes, so we know what the measurements at the top of the atmosphere are. What's happening in terms of the warming? So if you look at the sort of right side of the diagram here, or the right-hand side plot, the temperature, the black line here is showing the temperature increase at the surface, global annual average over the last, 170 years since the start of the Industrial Revolution. And you can see the rapid increase that's occurring over the latter part of the 20th century and now continuing into this century. And there are some other results which I'll go into later on, but that's the observed annual global mean surface temperature. And it's not just the surface temperature that's changing. Everything else that you'd associate with the warming is changing too. So it's not the surface only temperature of the lower atmosphere. It is the air temperature over ocean. It is sea surface temperature, ocean heat content, everything is increasing. Global sea level is increasing, air temperature over land is increasing. And then associated with the increase in warming, you would expect to see some decreases. So Arctic sea ice is decreasing very rapidly, in fact. Snow cover over land areas is decreasing. Glaciers are retreating in most parts of the globe. And global sea level is increasing. So you have a picture not just of surface warming, but you have a picture of multiple lines for a warming world.
How do you know that oceans are absorbing 91%? Is it measured?
Measured, it's measured. Yes, these are all measurements.
The 90% ocean.
Yes, is measured. Yeah, because this is up to a depth of 5 kilometers. You have measurements going on over all ocean basins. It's not global coverage, but oceans are pretty uniform. So you don't need a dense network of sensors to measure the heat going into the ocean. But it is going into the oceans.
Does it include the oceanic current?
Yeah, this is average. So you're averaging over all the dynamics or all the ocean. So the oceans.
Close this bar.
Oh, I see. Okay, sorry. So yeah, you have ocean currents, etc. But this is sort of look in the global picture, where the dynamics sort of washes out because of currents going in different directions, and you average them. This is actually the thermal aspect that you're measuring. So trying to understand this, we model the climate system, and just sort of go into some of the schematics of what the modeling looks like. So this is a picture of what we call the Earth system. So it consists of the atmosphere, obviously, the oceans, and you can see somewhere here, sea ice is here, and then there's the land ice somewhere, and then there is land. So it's sort of, and then there's ecosystem, basically the marine ecosystem and land ecosystems. So this is how actually we do the Earth system. And to just, present what kind of goes into the formation of the equations describing not only the individual reservoirs, but also interactions between them. You have the atmosphere consisting of circulation, radiation, chemistry, and then interacting with ice and ocean, sea ice, ocean ecology, biogeochemistry, and ocean circulation. And then on the land side, you have plant ecology, land use, land physics, and hydrology. And increasingly now, we take into account land ice, such as the Antarctic and Greenland ice sheets. And the canonical picture of modeling is you split the globe into latitude and longitude, which is called a horizontal grid, and then the vertical grid, which is the height or pressure coordinates. And then within each grid, you encompass the system that you are trying to represent, the equations representing system, which are basically nothing else but covering the thermodynamics, the dynamics, the phase changes, and momentum transfer. So you condensing all that into a set of equations that then you are solving on a supercomputer. And this actually is a supercomputer that we use, which is at Oak Ridge National Lab in Tennessee. And then we get results like, so before I show you climate modeling results, just taking to stock, we're trying to explain the satellite radiation imbalance as well as the changes in the climate system. So we have to understand, why should the climate system be changing? Is there some force that are causing it to change? So you can think of 3 things. One is internal variability. So the system, is a nonlinear system. So you can have variability, and over, decades and century timescales, you can have changes. So it could be perfectly natural. Except that, I'm not showing it here, but the internal variability changes due to it that we estimate are very small. And this is not just from kind of one model or 2 models. It's no matter what model you take, the coupled atmosphere ocean interactions just are not enough to cause you a change that is of the size seen in the observations. Then the other thing that you can have is natural variations. And by natural variations, one of those included here is solar. So solar irradiance is changing. We know that from measurements since 1977, from satellite measurements, that it is changing. And we know from paleoclimate record that, the sun's luminosity is increasing. So, there's a source of, we are saying that there's a net input into the system. So it could be a source of net input. But estimates of the solar forcing, you see this tiny bar at the bottom here, is very small. Zero means there will be no forcing on the system, and negative means it will be cooling the system, positive means it will be warming the system. But solar irradiance changes are very small. So you can sort of throw it away as a cause for change. There's another natural factor which does cause perturbations to climate, and that's volcanic aerosols. When the volcanoes go off, when the gases go off and they condense, they form particles which reflect sunlight. So it actually would act as a cooler to the system. Now, that is episodic. So the last volcano we had was in 1992, the big volcano, where you actually have stuff going to the stratosphere, where it tends to stay for a long period of time. So it can have a perturbation on the Earth system. In fact, it did. But the volcanoes are not uniform. Prior to 92, it was in 82. There was 182, then going back at 61. So there haven't been many volcanoes that can cause perturbation system. Furthermore, if they cause any perturbations, they would actually tend to cool the system, not warm the system. So that's why that IPCC increasingly has assessed that it's the anthropogenic or the human-influenced causes that really play a part in the climate change. And among the human-influenced emissions, the biggest positive forcings are what's called greenhouse gases. So it consists of carbon dioxide, methane, nitrous oxide, ozone, and also some water vapor. Water vapor is just like a secondary product. It's not directly emitted, of course, in the stratosphere. And these constitute a big positive term. And then you have things which oppose it, which is the aerosol pollution. So this is also anthropogenic. It's the pollution from aerosols, and it consists of a lot of different types of aerosols. It could be carbonaceous, it could be sulfate, nitrate, but they basically cause a negative effect on the system. That means that radiatively, they tend to cool the system. So the net effect of these two is depicted in this total anthropogenic. So you see it's a large red bar, but you see a big uncertainty there, which is coming from the uncertainty in the aerosol part of the story. So you see uncertainties in the greenhouse gases, and that's not, sorry, I went back. That's not very uncertain. Aerosol thing is uncertain, so it tends to get reflected. So that causes a bit of uncertainty in our estimates of climate calculations of what these forcings are doing. But nevertheless, the evidence is very strong that it's a net positive, but just with a large uncertainty. So what are the impacts? So now this is where the numerical models come in. So now with models, you don't have a second planet Earth, like a laboratory, to do tests on what will this do, what will that do. So you wish you had a lab where you could take just CO2 and say, okay, if I increase CO2 over the last 100 years, what would I get? Or if I take aerosols, if I increase over the last 100 years, what would I get? Unfortunately, the real Earth doesn't allow you to tease that out. And in a lab space, like if you're a physics lab or a chemistry lab, you can actually do these experiments, like take one thing at a time. But this is a large scope problem. You can't replicate the planet Earth in a laboratory, but you have the numerical recourse to it, which is a supercomputer. You can work on supercomputer and ask the question, what if greenhouse gases only were increasing over the last 100 years? And then what if aerosols were increasing over the last 100 years? And that's kind of what this calculation shows. So if you see the pink curve, that would be the change in the global mean surface temperature if only the greenhouse gases were increasing. And this is carbon dioxide, methane, nitrous oxide, and ozone. If the pollution aerosols only were increasing, you would see actually a decrease because, from the previous diagram, you saw they tend to cool the system. So it would be the green curve. In actuality, what the numerical calculations show, and there are some other forcings, I will not sort of go into that, but the net result is this blue curve, which is almost a linear addition of all the forcings. Now, that's kind of not a priori given, but it turns out to be almost a linear addition. And the black curve here is the observed, which I showed before on an earlier plot. And so ideally, if the model were perfect, that's what should be following. But the models are not perfect. But if you look at the rate of increase over the last, especially 50, 60 years, the rapid increase in observations, that is actually mimicked by the combination of all the forcings. It is not mimicked if you consider increases in well-mixed greenhouse gas alone. So clearly, there's been an offset of the effect of the well-mixed greenhouse gases, at least from a modeling sense. And that's because of the effect of the aerosols, which have gone in the opposite direction. And in fact, in this sort of block, I've listed here what the greenhouse gases have contributed over the last 150 years, which is 1.5 Kelvin in terms of changing temperature. Aerosols have contributed minus 0.5 Kelvin. So there's been an offset of about a degree in terms of the relative effects. Now, this is from the IPCC, where you can, and it's actually from a 2013 report, where you can show that over all continents, the forcing that you use for comprising of natural and human influenced explains the observed curve over all continents. So the black curve is the observation in all continents. The blue curve is what you'd get from just the natural aerosols, natural forcings, both solar and volcano, and that's a net zero almost. The blue curve is almost zero, no trend. And then the pink curve is when you include all the forcings, natural and anthropogenic. And so what this is, the envelope here represents the results from several models. There are about 40 different models which I've run. They're all different, not totally independent. Some of them follow the same prescription, but they are independent in the sense that they have parameters which are different from each other. So the envelope of increase represents the best estimate or the best attempt to explain the observed increase. And you can see that the net result is actually one of an increase as shown by models in terms of the explaining the observations.
Are there any places which have more than 1 degree centigrade also?
Yes, parts of Africa are more than 1 degree, but just about reaching 1 degree till this is showing up to 2000. So yeah, up to 2000 it's only 1 degree. Yeah.
70s, most of these figures like North America, Europe, Africa. So did any change happen during that time, 1970s or 1980s?
Aerosols. I'm not showing that. I can't prove that to you because I don't have the figure in front of me, but it is due to the increase in aerosols, because prior to the Clean Air Act in Europe and in North America, the aerosols were just continuing to increase because of sulfur burning, sulfur emissions. And so that caused, we don't know because there were no measurements of aerosols actually, but there was a lot of pollution during this, so much more than what you see over the Northern Hemisphere today. And we suspect because of the aerosol. There's actually another reason why I mentioned aerosols, you will see later on, because the aerosols had an effect on the rainfall too. And so the dip is, there's no other likely source for it, excepting either natural variability, which is plausible always, but the natural variability here is just not too much to explain that kind of a dip. So it's more likely aerosols, but it should be regarded as a hypothesis. We don't have measurements. Could be, but you're looking at we're looking at big averages here over like continental scale. So regime shift may not be able to explain every continent on this. It may explain over, like, for example, Western US, but not the entire US because the Pacific changes. Over Europe, less likely. So, yeah.
Now, all these models, they are dependent on the climatic condition, and not extraterrestrial, but let's say atmospheric condition, right? Atmospheric means model of the atmospheric condition.
Model of the physics of the atmosphere, right?
Now, that model itself, as we know, is not really a developed, a saturated model. We cannot use like direct numerical simulation for computing the entire atmosphere, but we use force models. How do these models affect this linearity that we observe here? Because in reality, the phenomena are non-linear, but the trends show linearity.
Yeah.
How much error it incurs, and what's the R square kind of error that?
So there are always uncertainties. I won't call it error. There are always uncertainties, but this is a coupled model. So when you do the equations, everything is free flowing. There is no constraint on what the atmosphere should do. So we don't have to borrow. I mean, you don't drive the model by using observations of circulation. The model develops its own circulation. The question is how realistic it is. And, in sort of a lot of the tests, before you use these models for climate change determination, you actually analyze how the present state of the system is reproduced, for which you have observations. And that's fairly good.
The fluctuations are well captured.
So fluctuations not on interannual timescale, perhaps. But long time scales, yes. So in short timescales, as you get closer and closer to weather timescales, you are affected by a lot of things that you can't really capture. But when you're looking at climate, where if you define climate by something on the decadal scale, then those kind of things don't kind of affect the trend that much.
Certainly, this is like spatial temporal averaging effect. Spatial temporal averaging.
That's right. That's right. You can do, because when you do averages over long time scales or large space scales, the thermal effects start to matter more than dynamics. And so the dynamical effects are still there, but they kind of recede as you kind of go to these longer, broader spatial and temporal averages. Yeah. So over India, this is the same model calculation. You can again ask the same question about what if the forcing was by greenhouse gases only, and see all the browns and reds, which is more than a degree over the entire period. So this is over the 170 years period. With aerosol, you do sort of get a broader cooling or less warming, and then I'll not consider other forcing that are small. And so the net effect is this all forcing case where you see sort of warming, net warming. So again, if there was only greenhouse gas increase, that's the picture that you would see. But instead, the model is presenting a picture which is less warming so far because of this nullifying effect from the aerosols. Let me just shift. I'm kind of going to actually focus more on the hydrologic cycle. So I've talked about surface temperatures, which is, I think, in a much more robust state in terms of understanding than the hydrologic cycle is. And the hydrologic cycle is sort of the real kicker in this problem, because it is actually so much also closer to human scale problems. So this is just a schematic of the hydrologic cycle. You have evaporation from the oceans, and of course you have precipitation over both oceans and land. And of course, there's a lot of things happening in hydrology, such as below the surface. You have the effects of soil, you have the effects of the water table, and then you have groundwater flow, and then you have stream flow. And then you also have the ice system, water storage in ice and snow. So there's a lot of things happening to water, both in the atmosphere and in the ground and in the ocean. But the basic thing is just evaporation and precipitation. I'm looking at it just from sort of those two viewpoints for the purpose of this talk. So the same model, if you look at what happens to the global mean precipitation change. So this is global mean, annual mean precipitation change. Again, you can ask the same questions. If it was greenhouse gas only, you would follow this curve. And over this period, you should have seen an increase in terms of precip. I'm interpreting this in terms of flux units, watts per square meter, but don't worry, an increase is an increase, no matter which units you measure it in, millimeters per day or watts per square meter. With aerosols, you see the sharp decrease. And then the net is given by the blue line, and the black line is an estimate of the precipitation. Now, precipitation is notoriously difficult to measure. First of all, you don't have gauges all over the world, like temperature sensors are all over the world. Temperature is a much more homogeneous, uniform variable. You measure temperature here, you measure temperature 50 kilometers from here, they're about the same. They're not varying that much. But precipitation, it can rain here in Kalyanpur, but it may not rain in Unnao. That's the kind of difficulties you have with precipitation. And so, but this is a construction of observations, and it shows sort of maybe a decrease and then, gradually an increase. We need sort of more years to figure this out, whether it's actually an increase or not. And just to sort of explain this in terms of, an overall sense, that's what I'm kind of going to try to do here. So if you look at the precipitation change, again, you ask the question, what is the contribution to greenhouse gases? What is the contribution to aerosols? What is it when they're acting together? So in the global picture, you see this cancellation, almost cancellation, which I forgot to mention in the previous diagram. You see the change here over this period. It's 2 watts per square meter in terms of greenhouse gases and minus 1.8. So the compensation by aerosols on the hydrologic cycle, in this case measured by the evaporation parameter, precipitation parameter, is actually much more sort of complete than it was for the temperature. The temperature, aerosols are offsetting greenhouse gases, but the overall trend was one of warming. Here, you're actually having almost a cancellation. I have to quickly add, this is, of course, a result from one model. So, you've got to kind of look at several models before this becomes a more robust result. But actually, all models show the decrease in precip occurring due to the effect of aerosols relative to that of greenhouse gases.
These new numbers are because of including clouds in the radiation budget, right? Yes.
I mean, clouds are always included.
Why the number? here, just previous slide. The previous, yeah.
Yeah.
Why this has changed, the precipitation included. That
No. Oh, sorry. This is precipitation measured in energy units. That was temperature measured in degrees Kelvin. Okay, difference. This is I'm talking about temperature here, and the other one was expressed in watts per square meter, which is flux units. But I can translate that into millimeters per day. That's a simple conversion. I think it's forget the number, but it just converts to easily. So this is a different. It's looked at differently. Precipitation looked at differently than temperature. So, but no matter what units you use, watts per square meter or millimeters per day, you get this exact cancellation. Yeah, so that is an important point, that you get a more cancellation in the precipitation due to aerosols than you do in temperature, and I'll tell you why. It's what I want to get into. So you see, this is the global annual mean precipitation change 20th century. You see this sort of cancellation for the global, in the global sense, and let's not worry about the other regions, excepting that Asia, you see a larger effect due to aerosols, and that's because of the larger presence of aerosols over Asia. And this is basically, the Indochina regions as well as rest of Asia. You don't see much in the Europe and North American sectors. Okay, so now to try to explain that and to kind of really address Sachi's viewpoint, let's look at the surface flux balance. So I've looked at the top of the atmosphere imbalance. Let's look at the surface balance. So this is a picture. That's almost the same picture. It's a little bit of different numbers, but the same picture. You have, at about 235 watts per square meter net coming in due to solar radiation, and net outgoing is balancing that to about 235. What happens to the surface is important. So without any perturbations, the net short wave is about 168 watts per square meter. That's kind of what's coming at the surface. The surface has to do something to compensate for that energy. So and the net long wave, there's also a back radiation due to all the absorbers in the atmosphere, infrared absorbers, and that's 66 watts per square meter. Minus 60 because what's happening is the surface is exporting more long wave. It's emitting radiation, receiving some, but the net export is minus 66. So the balance, the surface has to export about 102 watts per square meter in some other way to balance this net radiation deficit at the surface. So 168 minus 66 gives you minus 102. And that comes out in the form of sensible heat and latent heat. That's the way the surface has to be in balance. And it turns out that the ratio of latent heat to sensible heat is about 3. So the surface exports more heat due to latent heat of evaporation than due to sensible heat flux. So kind of an important point to bear in mind, because the explanation of why the aerosols compensate for the greenhouse gases actually rests on that. So here's the surface flux changes in the 20th century. From, again, I caution you, this model, but the physics works in the same way in every model. So if you take the well-mixed greenhouse gas case, so this is just the gases increasing, they're infrared absorbers. So what happens is there's sort of radiation coming to the surface in a long wave, and the surface acts to so it receives radiation in a long wave, it gets more energy, it has to get rid of it. So the change occurs in the form of latent heat of evaporation. So there's more evaporation. So more radiation down to the surface, there's more evaporation. And that leads to more precipitation when you have only greenhouse gases. Go to the aerosol only case. Now what happens is the short wave gets reduced. This is the important difference between aerosols and greenhouse gases. The aerosols reflect or absorb short wave radiation in the atmosphere such that there's less going to the surface and there's less available to do the evaporation part. So there's a net decrease of short wave. There's a sort of a small change in long wave, but that short wave deficit is made up of by the fact that evaporation is decreased. So the latent heat released on the surface is reduced because the surface now is gaining heat, because it doesn't have to release that much latent heat because it didn't receive so much short wave. And that explains the deficit in precipitation due to the aerosol. When you put them all together, which is in the all forcing case, things work out almost linearly. You have a deficit in the short wave because of the aerosols. You have an increase in long wave at the surface. So the surface is gaining energy because of the greenhouse gases. And then the latent heat is actually very small. So that's why the precipitation offset is almost so complete in the case of the aerosols. And in the case of aerosols, offsetting the greenhouse gases.
the resolution of the model the forest and canopy.
To the extent the model represents, yeah. Yes. So as I said, as I gave the answer to the earlier question, before you use these models, you test them for how well they are simulating this present day system. So, they're not perfect, but they simulate most aspects of the climate system, present day climates, observed climate system pretty well. So you have confidence that what they're doing is, maybe quantitatively not exactly correct, but the principles are what's
showing that with the large aerosols, it has a very different kind of, feed
exchange. Yeah.
into the interplay between the sensible and the latent heat flux because of
Right.
some effects on the photosynthesis.
Yeah. So the photosynthesis effects may not be accurately captured here, but in a very broad sense, this is something that has to happen due to aerosol reducing short wave. Therefore, the surface kind of reacts in a way that would be consistent with just sort of thermodynamic laws. So this observed decrease in precipitation and observed changes in short wave. So this is actually now from observation. If you look at the black line, there is the observation of the northern hemisphere summer short wave radiation anomaly. So anomaly means difference from normal. So you actually see a decrease in the short wave in the northern hemisphere coming over the 70s and 80s. Goes to your earlier question about where we think the aerosols would have caused a decrease in temperature because they actually decreased the short wave radiation. And this decrease in short wave radiation is due to aerosols, it's not to clouds. And now it's kind of increasing as we are approaching beyond 2000. But this is kind of the picture. And the red and blue are models. So let's not worry about models here. So all the models actually follow that curve. They're decreasing, but not the same rate as the observations. And then the bottom curve shows the precipitation change over the northern hemisphere. Sorry. And you can again see the black lines. There are two different reconstructions. And you see the decrease in precipitation from about, very prominent from about the 60s to 80s and into 90s, and then starting to recover. And again, the red if you look at the red curve, that is with all the forcings, and you see that the models, the average of the models, so this is a lot of models together, are actually showing you that decrease happening. Actually, it's not as pronounced as the observation, but it is showing you that tendency to decrease. That bottom line is that if you are doing calculation with just greenhouse gases, which is a pink line here, you would see an increase. So you don't see an increase, so that the system hasn't really followed all the way of the greenhouse gases. So something has offset it, and the most plausible reason, it seems, is the pollution aerosols. Black lines are observations. So which one is the top panel or bottom? Both of them.
Bottom panel.
Both the panels, yeah, they're observations. So this observation of short wave radiation of the surface. Okay, so that's the solar radiation coming to the surface. And this black line is a precipitation in the northern hemisphere. So both of them are showing a decrease, which is, physically consistent with one another in the observations. And so the models are also following that kind of trend, even if it's, not exactly quantitatively the same. And again, over India, if you look at the precipitation, you see sort of the greenhouse gases will tend to increase precipitation, which is the brown and red lines. The aerosols, which is this one, shows you a decrease, which is kind of to be expected from the slide arguments, the previous slides. And this is the net. So actually, in the net, if you look at just the bottom panel here, as I know it's very sort of a lot of lines here, but the observed trend lines for especially the Indo-Gangetic plain is this sort of black line here, or you can see the sort of straight line drawn through the observations, which actually shows a decrease. Whereas if you see this red curve here, that would be if only greenhouse gas were increasing. So even over this very sensitive region, the Indo-Gangetic plain, there's been a decrease in terms of the precipitation in the last, actually this is only till 2000. So till about 2000, there was a decrease. So since this is sort of a uniform thing, it's not aerosols haven't done something just in one place, it's all over the place. Asia has been particularly important because of the larger presence of aerosols here, but it's not a local effect. It's sort of this is a global effect and communicated to all regions, even though the forcing may be preferably in one place.
So it refers to March, April, May month.
This is March, April, May. No, it says it's like March, April, May, June, July, August. So going through the summer, monsoon period, in the monsoonal period. Yes. So actually, there's a lot of evidence now. I mean, there have been other papers since this was published in 2011. There are other papers now which kind of are showing this trend now from different points, different observational perspectives over really all parts of northern and central India over the last till 2005 to 2010. Now it's kind of flattening out or even increasing back to normal. And associated with that, some sort of another study we did was the monsoon depressions, and this is from the ERA analysis. So it's a reanalysis from observations. So consider this as observations of the monsoon depression around 20 degrees north, which is kind of where these form. And this is from the model, the same model results I showed. And there's actually a consistency in terms of the depression forming and the forcings that have been acting on the system. Okay, 21st century. So now we're coming to the future. So if the physics of what I just said, over the last few slides is correct, then what we should see is in the future, when we expect the scenarios call for the greenhouse gas increases, continued increases. I mean, I know that there's a lot of thoughts about net zero, but for the moment, this really the scenario is one of an increase for some time. But aerosols are definitely going to decrease because of the abatement methods, the technology that's been applied really is saying that the aerosols are going to decrease. In fact, that is being noticeable already in the global atmosphere, that aerosols are decreasing, perhaps not so not so discernibly over Asia, but certainly over North America and Europe, they're decreasing. Okay, so that means if aerosols are decreasing, greenhouse gas is increasing, we should get the reversal, right, of the effects. And indeed, you see that happening. So let me just sort of go to the temperature. So here we are in 2000. So this is where to almost 2010. And these are curves that you saw here before, the pink curve and the green curve is the aerosol. But now as the aerosols decrease, their effect starts to go down. And as their effect starts to go down, this blue curve, which represents the sum, starts to approach the greenhouse gas solution. This is from CMF6. Six, yes. So the CM4 model that we use was CMF6. And so you see and this is the observation till now. So what we should expect is that this blue curve is going to rapidly get away from the aerosol solution towards more the greenhouse gas only solution. And indeed, that's kind of what. The more interesting thing is, okay, this is the sort of temperature change. I'll skip over it in the interest of time because I want to sort of focus on the precipitation more. And again, the precipitation case, again, the aerosol effect on precipitation, now it's actually millimeters per day, is decreasing. The greenhouse gas, on the other hand, is increasing because the scenario is one of increase. And the blue curve is again rapidly approaching the sort of pink curve. These are two observational reconstructions. You can see they're not identical with each other, which is a problem with precipitation observations, but they're not necessarily increasing at the rate of the greenhouse gases. They're kind of still somewhere here. In fact, if anything, this particular reconstruction, the solid black line, is actually still showing a decline, but it's actually again starting to increase as the dotted curve, which is another reconstruction. So both of them are going to start increasing. So this is sort of the sort of and sort of an irony about the precipitation, that it might actually start to increase pretty dramatically with these scenarios of greenhouse gas increase and aerosol decrease. And so there's a rapid reduction of the aerosol offset of the greenhouse gas in the 21st century. So the question really is, how rapidly will this occur, which is going to depend upon what the scenarios are. Yeah.
Why is that between the solid and dotted line?
There are two different reconstructions. I don't understand the nuances between those reconstructions. They are derived from essentially, so one of them uses entirely GPCC, which is a satellite source. One of them uses satellite and rain gauges. I don't know how they parse it together. So that's the difference between the two.
So Professor, this is the 4.8 scenario or 8.5 or 2.2 scenario?
This is the middle of the road, 4.5. 4.5. So the story that is emerging, and actually now I'm looking at two different models from CMF5 and the one that we submit for CMF5 and one that we submit for CMF6. the main question is in terms of precipitation. Back in the early part of the 20th century, there probably was very little influence on precipitation because the forcings were not that much, at least due to the human influenced causes, that probably was not much. And then you have the situation here over between about 60s and going up to 2000, where in the Northern Hemisphere particularly, the aerosol effect may have been actually comparable to or even exceeding greenhouse gas effects. But then as we go into the future, the greenhouse gas effect is going to become more dominant. So there was a period of decrease and followed by rapid increase as we go towards more 2100. If this is, if this story is holds true, what I think is then a sort of thing to reckon with is how we may not have been able to really see the signals of greenhouse gas changes in precipitation so far because of the huge effect that aerosols have had on this whole physical system. And that's kind of maybe one reason why the signals have been so hard to detect, because there was an offset in the force. That's just a provocative question. Maybe it wasn't, but the aerosols definitely have had an effect in retarding the influence that greenhouse gases will have on precipitation, because the effect of CO2 on precipitation is well known from not just now. Back when the first models were invented back in 1970s, it was well known that the whole vigor of the hydrologic cycle would increase because of increasing greenhouse gases. And yet that has not been noticed so far. And is it because of the effect of aerosols? And then finally, we've been looking at the surface flux change, the surface heat balance. So if you compare 2100 to 2000, now you have the net short wave increasing because the aerosol effect has been taken out. So you have to have an increase in the net short wave. Long wave continues to increase because you're having continuous increase in greenhouse gases. And now the latent heat change has to be more because now both short wave and long wave relative to 2000 are going, well, the short wave is going the opposite direction. So it and long wave both add together and you get a larger latent heat release and therefore the larger increase in precip. Okay, so let me just conclude by talking about water vapor change itself and its significance, because I've started talking about the hydrologic cycle, which of course consists of evaporation and precipitation. Now, evaporation, if you look at the bottom right, that's the climatology in the model of the evaporation. And the dark red means more evaporation. So brown to red means increasing evaporation. You see the largest increases over the oceans. That's where the water evaporates over the climatology. So this is a natural cycle. The climatology consists of large evaporation from the oceans. So when you perturb the system, and let's go to the greenhouse gas case, top left, you see an increase in evaporation from the oceans. Now, the scaling is different, by the way, from the climatology, but the reds again show an increase, a positivity in the increase in evaporation. If you look at the aerosol only, it's the other way. It's a decrease in evaporation. And the net, is shown in the bottom left, where you have an increase compensated by decrease over the 20 years, 2000 to 2020. So it's just 20 years. But you see sort of the changes that occur in the evaporation cycle because of what is forcing it. And if you look at, sorry, yeah.
This actually near the African soil, the South America, there are white spots.
Yeah.
See.
So white means very small change.
Beaten with water.
Which panel?
This is top left. Top left.
Okay.
There are a lot of white spots also in the water, like evaporation part which
Right.
takes place.
Right.
Why?
Because if there's downwelling, you can suppress evaporation, but it's not zero entirely. I mean, the shading is about -1 to +1 watt per square meter.
Such a low evaporation rate.
Oh, because if you have downwelling, if you don't have upwelling, if you're downwelling from the atmosphere, you would actually reduce evaporation compared to regions where it's upwelling. And also it depends, on mostly it's that, and that comes about because of the flux exchange depends on the airspeed, depends on the pressure, partial pressure of over the air and over the ocean. And if the downwelling is there, it suppresses the natural tendency to evaporate. But it's not zero, because it could be plus 1 watt per square meter, because the white is just very small values. I mean, if you draw the significance on this, anything with plus minus 1.5, you can sort of throw away, because that's really noise. So one of the consequences of the evaporation is that water gets into the atmosphere. And there's an increase. I mean, there's water coming out of the atmosphere too due to precipitation, but water increase in the atmosphere. And you can see the increase in specific humidity, that's the amount of water, in looking at the red and the black curves. So the red curve is only for the greenhouse gas changes, and the black curve is for the 2010 is greenhouse gas only, and the red curve is for all the forcings. So because of the aerosol effect, you actually decrease the amount of water entering the atmosphere. But on the other hand, if you increase greenhouse gases, you're going to see continued increase in the water vapor building up in the atmosphere, and most of it is in a region in the upper troposphere, which is actually a very sensitive region for water vapor feedback on the climate system. Let me go to sort of explaining something else here. So when CO2 increases, you can partition the effect on climate in three sort of stages. The first stage is a direct surface heating by CO2. So if nothing else changes and you are increasing CO2 molecules in the atmosphere, the surface heats up because there's sort of increased long-wave radiation. CO2 is an infrared absorber. So if you change nothing else in the atmosphere, the heating at the surface will increase because of the CO2 changes. That's not part one. Part two is when the troposphere heats up because of the heating of the system. And now the CO2 direct effect consists of increase in molecules as also increase in temperature. So the two together will send more radiation to the surface. That's stage two. Stage three, which is the most important one, is that the CO2 heating increases forces more water into the atmosphere because of evaporation. And that is the biggest contributor to the whole problem. So if you look at, for example, this total here in watts per square meter, in terms of temperature change, let's look at temperature change. This is a very simple model. I mean, there are issues like cloud feedbacks, etc. But just looking at water vapor alone, that water vapor feedback alone increased the temperature change due to doubling of CO2 by 2 degrees Kelvin, 2.2 actually. The process 3, which I've called, which is the increase of water in the atmosphere. Water is a very strong absorber, very strong greenhouse gas absorber. In fact, it is more strong than CO2 because there's lots of it, lots of water vapor than CO2. CO2 is in parts per million. Water vapor can be more than that near the surface. So the latent heat effect due to water vapor evaporation is 1.7 degrees Kelvin. So about 70 to 75 or greater effect is coming from water vapor, which is why the effect of increased greenhouse gases in the atmosphere, led by CO2, is actually going to pump up more water just by law of thermodynamics. It's got it. And in fact, if you look at the climate feedback, so this is something that I'm not going to get into technical details of this, but in the IPCC assessment of climate feedbacks, where a feedback means something which amplifies the original signal. So there are two important feedbacks. One is called the Planck feedback, which is just the temperature. As you change the temperature, there's going to be more emission to space. So it's a negative feedback. The more temperature increases, the more radiation escapes to space. But the water vapor feedback is a positive. And these three curves, let's not get into details about them, but these are assessments coming from before, like CMEP5 and CMEP6. And the assessment is that it's a strong positive feedback, unambiguously. You look at the other feedbacks like cloud feedback, they can be slightly positive to a little bit negative, but water vapor and lab state feedback is a strong positive. So that is the whole sort of sequence here is CO2, well-mixed greenhouse gas increases, water vapor increases, and that's a strong feedback mechanism. In addition, water vapor does very weird things. Excess of water vapor causes a lot of calamities, a lot of losses, as well as deficit of water vapor also causes a lot of damages. And that's the part that we have a dilemma about on the whole hydrologic cycle, because as more water vapor gets into the atmosphere, it releases latent heat, which is a strong thermodynamic influence in the atmosphere. So the circulation changes, and circulation change may mean that some regions might not get more water. Some regions which were getting less water may get more. Some regions which get more water may get less. And that's the part that we still have to kind of tease out. And this collage of photos is just kind of showing real disasters where either excess of water or deficit of water actually matter in terms of loss and damages. All right, this is just I threw it in a diagram from the New York Times from August 2010, I think, 2019, which actually shows the increasing stress as you go into 2020s, 2030s, 2040s. Here, stress is a very general term. It means just, affects human lives. And you can see the reds increasing as you go from, keeps repeating, 20 to 30, 2020, 2030, 2040. So the stress from water is something that we have to grapple with in addition to the stress from temperature itself. And finally, I'll just end with this diagram. Now, this is kind of where an entity like the center, the Kesavan Center, really has to deal with not just the weather and climate side of the story, but also things like vulnerability, where it's a predisposition of a group or persons to be adversely affected. Like if you're living along some region where it's prone to heavy rainfall, and then exposure, if it's in the wrong place, the wrong time. And together, that kind of constitutes the risk that we have to look at from the whole hydrologic cycle. And I think that was more, just the concluding points. So aerosols have offset the greenhouse gas effects. The largest effects occur in the Northern Hemisphere because that's kind of where these pollution aerosols were. And in the Asian monsoon region, which is again where the largest concentration of aerosols is. And I think that's now the continuous cycle observations have shown that there's been a major shift in the relative imbalance, and it has had its impacts on climate. As we look into the 21st century, we are going to recover from the aerosol effects, which is because of technology and increasing concerns about health and visibility, which is causing countries to clean up their air. But this is going to mean that the whole physics now shifts to the other side, where the hydrologic cycle is going to increase in vigor relative to the 20th century. And the evaporation of water does two things. One, more moisture in the atmosphere drives extremes in the atmospheric circulation through condensation, latent heat release, and precipitation. And two, on a climate effect, it actually amplifies the initial greenhouse gas forcing, causing a very distinct feedback that is of concern, especially when you're talking about policies to adapt and mitigate. All right, so thank you very much for your attention. And welcome questions.
Few questions. I just want to know that from your the very beginning, ocean is taking up more energy. Does that have some consequences for the climate changes?
Yes, I mean almost all the extremes that you saw actually just in the images that I showed towards the end, they are all arising from the excess heat in the oceans. Sorry, I should say that there will be more tendency for that because of the heat going into the ocean. So the ocean-air interactions are a consequence, or the change in the ocean interactions are going to be a consequence of the increased heat into the oceans. And so you would have larger shifts in the circulation patterns, existing circulation patterns, as well as changes in the domains, in the spatial regions where these patterns occur. So the oceans play a big role. Yes.
Yeah. So the other point that I wanted to ask is, you have the ocean is increasingly clean, but at the same time you also show that the water vapor is also increasing. So what happens to the this is only the energy point of view. What happens to the mass as such?
What happens to what?
Mass.
Oh, it's even the water vapor build up in the atmosphere.
We also we have water storage on land and water storage in the atmosphere. So is your model showing some sort of
Sure.
feedback?
So first of all, observations in the atmospheric side of moisture is showing an increase. So there is an increase in the moisture content of the atmosphere. There's also an increase going over land and ice because of the, as the bigger the hydrologic cycle increases, you're going to have more precipitation. So there's going to be more water on the ice system, also on land. The trouble with land is that it is, it's first of all, the starting amounts are small. You're adding amounts to it. They just are not distinguishable right now in the records. Plus, you don't have measurements going well into the soil. So you have surface measurement, but that's not enough. You have to go deeper into the soil to actually record what is happening in the land. So we are not able to see that with the existing land measurements as to how much the water is building up in the land, as we do in the oceans. Oceans is easy. You can actually go down to several depths without any problem. Over the land, even in developed countries, it's difficult to kind of do it over all land surfaces. And then, of course, over the globe, you don't really have a coverage over all parts of the globe. You do have now the GRACE satellite, which is actually looking deep into the surface. And it's actually showing an increase in groundwater from satellite measurements over certain portions of the land. So I don't know what globally it amounts to, but it is showing an increase over land, especially over the last 20 years, which is when that satellite has been flying. So yeah, it is increasing over land, but it's quantitatively, it is not yet at the same certainty level as the increase over oceans.
Dr. Anubhav Goyal.
Sorry, I missed the earlier part of the session a little bit. So I just wanted to clarify that what I am interpreting from your excellent talk is correct. I understand that the level of water vapor in the air has been increasing, and it is amplifying the impact caused because of the greenhouse gases. So that would mean that the current models that are being used, they will have to be modified further to be amplifying the correlation or the conjugation of the two impacts, right?
No, actually, the current climate models, almost all of them, have this feedback effect. So it's not something that is missing from the models. Because this is sort of if you have a coupled atmosphere ocean model, this would have to be there is a consequence. If you did it otherwise, it would be physically inconsistent. So because there's an increase, because the Clausius-Clapeyron equation guarantees there's a 7% increase in moisture per degree of surface warming. That's pretty robust. I mean, and all models hopefully follow that physics. So I don't think any model is deficient in that respect. They don't have to add anything to capture this feedback effect. It is there. It's only that it has not been, I think, very vividly looked at in these models from a hydrologic cycle point of view. But it's there in every model, I can guarantee.
Is the impact that the El Nino effect we had in India after a long time last year, and they are predicting that over times to come, the monsoon pattern in India will change a bit further also. And we'll be having lesser rain over the years, over the entire year than we are getting generally. Is that going to be a repercussion of this feedback as well?
So, it's a slightly difficult question to answer because it gets into a lot of complexities associated with the region, especially if you're looking at seasons and different months in India. Overall, all the climate models actually predict a more vigorous monsoon let me not say monsoon, vigorous, more precipitation over the course of a year than has been the case in the past, because that's kind of what greenhouse gases should do. They should increase precipitation. But if you look at specific periods like monsoon, pre-monsoon, phasing of the monsoon, post-monsoon, that's a bit of a more difficult question because that starts to hinge on how well the models are capturing the regional circulation over different months. That's a more difficult question to see how that precipitation is going to be parsed out over the course of a whole year. But in general, if you're doing sort of decadal averages, all models do predict the monsoon will increase, except the only one difference is that some models will have the rain increasing over certain parts of India and not others. Some will shift the monsoon more towards Southeast Asia. Those are consequences of how the models are formulated. But overall, every model should really show an increase in precipitation. But there are differences. We're not at the level of perfection yet.
Thank you.
During modeling, all the forest area have you accounted. Also, there will be the density of forest will be different, in different terms. So that has also.
You mean like a feedback due to regrowth of forests?
No, sir, the original forest.
That's pretty. So as I said, these models are pretty good when you compare the present day climate similar to the model with the observed climate. So the land vegetation is, I would say, well represented. But just like I'm cautioning on all the other aspects, these are not necessarily perfect. We don't have a lot of things about vegetation that we should, like the growth of vegetation, dying of vegetation, regrowth. Those are not there. But in a global context, the regional differences like land vegetation, unless they are very, very seriously wrong, they are unlikely to change the nature of the solutions. Quantitatively, yes, they would all matter. Qualitatively, in terms of the trend in whether it's going to increase in precipitation or decrease, that should not have an effect on larger scales.
You have said that during initial validation, you have checked the temperature of the water in the oceans. How did you perform that experiment, sir, to check?
No, I don't measure the oceans. I rely on observations taken by other people of the oceans. We don't measure. Yeah.
Are there any more questions? I think one last question.
So, Professor, so as you told that these weather patterns like El Nino and La Nina is changing due to the sea surface temperature. So my question is that what are the impact on these weather patterns of these greenhouse gas and these anthropogenic aerosols in the future scenario? So can you comment on it more?
So first of all, on the El Nino, La Nina, the model still can't do a good job on shifts from El Nino to La Nina conditions. They can if they introduce El Nino temperatures, they can predict what the circulation will do. If they introduce La Nina temperature, they can predict what circulation will do. But the transition from El Nino to La Nina is still not there in most of these models. But that's an interannual phenomenon, you have to understand. So, that is not, again, going to have a big bearing on decadal scale phenomena. Now, about the variations in the atmosphere, one of the big consequences, and I don't have time to show this, but there's a term used, atmospheric rivers, these days, which is big clumps of moisture flowing in the atmosphere from wherever they started from and going, especially in the oceans, to land. Most classic example is from the Pacific Ocean. Big clumps of water go towards the Western US over California. And there's also over Africa, which hits the African continent. So with the increase in moisture, we do notice from the same models that the moisture content of these sort of so-called atmospheric rivers increasing, which also sort of leads to another thing, which is that more moisture, the atmosphere now has more moisture holding capacity because it's increased its temperature, and by the Clausius-Clapeyron equation, you should have an increase in water vapor pressure. So water vapor increases in the atmosphere, and what it does is that builds up big clumps of these moisture wells, and when it rains a lot more than it would have before the atmosphere was filled with more moisture. This is something we can't show, in a signal to noise analysis, still there's a lot of noise, but it looks like the extremes in precipitation events is actually on the increase in many places around the world. I mean, the rainfall over Bombay in Mumbai a few years ago was a classic example. Rainfall over Chennai a few years ago was an example. Those kind of things I've never seen before. And even over, in sort of recent passing of a hurricane, Hurricane Ida, was it? Yeah, coming from the Gulf into the southern part of the US and then kind of going out to the northeast as a storm. It dumped more rain on the land part than when it entered from the ocean. So it had moisture coming in from the ocean, but it somehow dumped everything interior. And that was so unexpected because heavy rain was forecast, but not that heavy rain would fall within the space of just 1 hour. So these kind of extreme events are increasing, which is kind of addressing, I think, partly your question of what it does to the circulation, because the circulation now has to deal with more moisture. So these rapid downpours, rapid torrents of rain are increasing almost everywhere. Well, almost not everywhere. A lot of places, especially in the Northern Hemisphere, and even in Australia, there have been lots of events of increase in precipitation. So this was not seen before. So now the question is this due to the buildup of moisture in the atmosphere or something as a consequence of that, or is it a different reason? We don't know because the signal to noise problem is still there in the analysis of these, but the extremes are becoming very noticeable, as you can see. I mean, reading the news media, etc., that they are very noticeable. So, sorry to be long-winded, but
Thank you, Ramaswamy, for the wonderful talk. And if they have questions, can you get back to you?
absolutely. And I can give my email, so please feel free to write to me.
Feel free to write to him if you have any more questions left. He has to head to city. After this, he has come for his school reunion. He studied in Methodist school at Kanpur. So thank you so much for your talk. As a token of our appreciation, we have planted a tree for you. Just once again.
Nice.
So this tree has been planted in your name. Yes.
Lovely.
Sorry. I don't know what is happening.
Should close again.
So you have an idea, no? Is it?
Yes.
Oh, wow.
So let me just share. I don't know why is it not. Just once again.
Oh, wow. No, amazing. This is it, right? This part?
This is in Pune, the Chandrakanta group.
Okay.
Chandrakanta Center group. There is a in Pune with.
Okay.
So for some reason it's have you disconnected from there or what?
Yeah. It connected to and
Okay, just once again. Yeah, it's you can see, yeah.
Oh, okay.
So this is the tree that we have planted.
Yes. It's so nice. Okay. It's so nice. Thank you. Thank you so much.
Can we have a picture of you
Yeah.
with the tree?
Yes.
Maybe you can stand beside and Mohan can take
Where's
it.
yours? These were so nice. Thank you. That's a wonderful.
And we'll send you the link.
Yeah.
So that
The mail has already been sent to you.
Oh,
okay. So it has gone to your mailbox, and you can see its growth as a function of time. Okay, thank you very much. Thank you so much.
Thanks very much for attention.
Forest is done, so it is taking time, but
Okay.
it's already been planted.
I have an idea.
Thank you all the online participants. We are closing the session now.
Thank you so much. Nice questions.
Stability, that how is that having very positive? Is it trapping mode? Now you see the change in the last rate as a positive effect. If you have also trapping mode, what